with all of the work that we've been doing with weak acids and weak bases and buffers, it all came down to things being weak. And weak is dealing with equilibrium. Our textbook finishes this unit by relating equilibrium to solubility instead. So equilibrium, a huge topic within AP Chem. In Chem 1, we go over equilibrium a little bit, that back and forth reaction. We talk about Le Chatelier's principle. You definitely need to know that. But then you started doing math this year. You do a KC to solve for the equilibrium of a concentration for just any random reaction. We actually did that with the spectrophotometers with, I think, an iron thiocyanate ion. We do a KP if it's equilibrium for gases, for pressure-wise. Then this unit, we did Ka, equilibrium for acids. Half of you turned in the lab report where you solved for that. Hopefully you got around 1.8 times 10 to the negative fifth. So that's the Ka of acetic acid. Some of you solved for Kb, equilibrium for a base, which, if it was ammonium hydroxide, it's actually the exact same number of 1.8 times 10 to the negative fifth. What we have to introduce today is the last K, Ksp. Sp stands for solubility product, just like I have written up on the top of this slide. It's still an equilibrium math problem, which you do need to remember equilibrium math problems. And the nice thing about doing this is we have to remind you once again of ice tables as we're doing some of this. Because there are questions that are just, what's the pH of this weak acid given this molarity, which you need to do an ice table for. Okay. For example, if I were to dissolve something, because solubility is based upon dissolving. If I were to dissolve sodium chloride in solution, I can make sodium chloride solution. At some point, if I keep on adding sodium chloride solid, I won't be able to dissolve anymore. In Chem 1, we talked about that being a saturated solution. What is really happening is what my bullet point is stating. If I keep on adding more solid silver chloride, it's not a matter of that solid won't dissolve. It's more that it's at equilibrium. Some of the solid will dissolve, but as some of it dissolves, some of the solution silver chloride would undissolve. So you'd have this back and forth. And that's where we can write down an equilibrium expression to show that. Again, I'm omitting the water. Water could be drawn above the arrow, I guess, if we wanted to. But remember, water has no concentration that we need to worry about when we do our math, so it's not necessary to include that. So if I have silver chloride solid, it can make silver ions and chloride ions in solution. And at some point, there will be a balance between how many of those ions can be dissolved and how many stay as a solid. If I were writing this to solve it mathematically, I would just have my K equal the concentration of Ag plus times the concentration of Cl minus. Now the very last thing you don't have to write down in italics is more a reminder of me to ask the question to you guys. If K is products over reactants, why am I not dividing this by the concentration of AgCl?
AgCl doesn't have a concentration because it's a solid.
Solids don't have concentrations. Aqueous and gases, those are the only things that we would ever have values for. So the good news about the equilibrium math that we are going to be doing the next two class periods is there's almost never a denominator. You're not going to divide by the reactant because the reactant is a solid. Unlike weak acids where you do have to divide by that. Where you will typically see stuff like this is in multiple choice. Because they can give you numbers that are nice and even and round where you can just solve for the KSP. Your free response is usually focused more on weak acids, buffers, things like that. Titration math, titration stuff in general like we've been going over. The K stuff for solubility product lends itself more into the multiple choice realm. I think that's true not only for the testing that I'm giving you in a week, but then also college board wise. Because equilibrium covers so many dang things. that they want to make sure on the free response you hit the most important part of it. Here's a second example. Magnesium chloride. Magnesium chloride is actually a lot more soluble than silver chloride is. Here's how I'd write that expression. Remember, just like when I introduced equilibrium to you way back at the beginning of this semester, you take the concentration of things and you raise them to their stoichiometric coefficient. That's why the CL is squared in this particular case. One thing I have on the slide that I'd like to mention, but I don't think you need to write down, is this expression assumes that ions behave ideally. And what I mean by that is if I have magnesium +2 and chloride ions floating around in solution, there is a chance, although low, that sometimes some of those ions can pair up. So you can make an MgCl+1 ion. Again, it's something that we never really talked about in Chem 1, and quite frankly, we don't really talk about in AP. Heck, you could have MgCl2 together being aqueous. You could have ions reacting with water. Remember Lewis acids and things like that. So we give you these equilibrium expressions, but I know one of the things that I'm less likely to ask you about, but the College Board might ask you about, is they like giving data. They like having you solve for something and then compare to what the real results were. Well, why did we have different results? So they like giving example questions that deal with you trying to explain experimentally what went wrong. Now that could be something as simple as, I think there was one test a while back where, hey, they didn't dry the solid created enough from the filter paper, and that's why the mass was less after day 2 than after day 1. It could be more complicated like this is referring to. But in general, that's what the K values should equal. Sometimes they don't equal out exactly what they should be. That's one of the sources of error. So, in Chem 1, we gave you a solubility table. All those S's and I's. S stood for soluble, I stood for insoluble. I know I told my students to highlight all the I's, and then you're kind of playing battleship when you do double displacement reactions. You're looking to get a hit. One of the I's to say that a solid made. If you've learned nothing this year in AP Chemistry, what you should have learned is I just lied to you a whole bunch in Chem 1. Chem 1 is a simple, simple world in which we let you live. Once you get up to this level, we have to break you down and remind you that life isn't as simple as Chem 1. It's a little more complicated. In actuality, every single compound that's an I on that table, it could be dissolved in water. Ionic compounds can be dissolved in water. The I's that are on that solubility table that you highlighted are the things that don't dissolve well. Actually, Mr. Butters the other day just came up to me and said, hey, the sulfate isn't really creating a precipitate with, and I forget what it was. Odds are we just didn't have it in a high enough concentration. And that's why it didn't create a precipitate. So much like strong acids have a really huge K value so big we ignore it, some ionic compounds have a large K value as well. For example, the dash NaCl and the KNO3, we don't have K values for, because NaCl almost completely dissociates in water. So does KNO3. On the other hand, there are some things that have small K values. And that's what our focus is going to be. So when you looked at that solubility table in Chem 1, and you saw that silver chloride, AgCl, has an I next to it, meaning insoluble, if you gave me a bathtub of water and a grain of silver chloride, I could dissolve silver chloride in water. It could be soluble. But a K value that's really small is really demonstrating what are those I's on that solubility table. So one way that we can do the work that we're going to be doing in the next couple of class periods is applying K to double displacement reactions. Because if I had a dilute concentration of sodium sulfate and a really dilute concentration of, I don't know, barium nitrate, I could get those two to mix with each other without creating a precipitate. That K value is going to tell me what concentration do those have to be at in order to create a precipitate. Because if they're really dilute, those ions might not even interact with one another. Because that's what has to happen. Ions have to come together to build up to create that precipitate. If they don't, then they won't create a precipitate. It's all about that level of attraction. Usually higher charged ions are more likely to attract to create that precipitate, but even if they are highly charged, if they're really spread out, diluted, they still might not be able to find that other ion to be attracted to. So again, one way we're going to do this is with double displacement reactions. You'll write out reactants, you'll write out products. Yeah, you can look at your solubility table to figure out which one is insoluble, but more likely what's going to happen in that style of problem is it's going to give you a K value for that product, and then you're going to see would it create a precipitate or not. The second way we can use this is kind of back to the first slide where I gave you a picture of solubility charts. We can tell whether or not a solution is going to be saturated, unsaturated, or supersaturated. So my first example went back to silver chloride. You keep on adding until it can't dissolve anymore, then you reach saturated. We can solve for whether or not a solution is unsaturated, saturated, or supersaturated mathematically. In Chem 1, we said we couldn't do that. You just look at a chart. Are you above the curve, below the curve, or right on that line? Lies, I tell you, all lies. If I gave you an amount of solute and an amount of solvent, I could just ask you, is it saturated, unsaturated, or supersaturated? At a specific temperature. Remember, solubility is temperature dependent. And in Chem 1, you're able to look at a graph and just tell, here it is. But if we don't give you a graph, you can still figure it out. Because you can solve for what's called the reaction quotient. Something that we covered when we introduced equilibrium. Something that we did not have to do with weak acids. Determine which direction the reaction goes. Remember, that's what the reaction quotient was, is K bigger than Q. The caret kind of is like an arrow. If I am given a K value, because K values are known values. They are for weak acids. They are for solubility as well. And if I solve for Q, so products over reactants at some time, which again, products over reactants, you don't even have to do the over reactants for this part. If the Q is less than K, that means I have less ions floating around than I could actually hold. That makes it an unsaturated solution. If Q is equal to K, that means it's a saturated solution. If Q is greater than K, I could have a supersaturated solution. Or in terms of double displacement reactions, at that point, I could create a precipitate. So these first few slides are all trying to relate solubility product to all the other equilibrium type stuff we've done this year. There are two different ways that this can be applied. Again, saturation level, which is what this slide is kind of referring to, and then whether or not double displacement reactions will occur, which was the previous slide. My next slide is going over mathematically what are the steps that we have to take in order to solve this type of problem. And then I wanted to finish notes with two sample problems of this. So I'll give you practice to show you how it's done. Because again, you guys today get it done in 15 minutes. We'll see how much time you have left to work today. It might not be a lot. Okay. This actual diagram in blue on the bottom of this slide, our textbook uses. So if you look at our textbook at the end of this acid-base complex chapter, it gives you this. Molar solubility is referring to the number of moles of solute that can be dissolved in a solution. Good solubility, the ability to be dissolved. Molar is kind of a concentration. So what concentration does something make when it's saturated? Is what molar solubility is referring to. Solubility is not referring to the moles of solute, it's referring to the grams of solute. So if you look at this chart, if I gave you the solubility of a compound, I could say something like silver chloride can be 0.3 grams per liter dissolved. That'd be the solubility. If I give you grams per liter, you should be able to convert to molar solubility, moles per liter. Use your periodic table, do a mole conversion. Then we can solve for the concentration of anions and cations, and eventually make our way to solve for the K value. Now the math that we're going to be doing probably in our practice sheets will require a calculator. However, like I said, if it's multiple choice, it's going to be numbers that are nice and neat and round. That'll make it a little bit easier for you to solve for. Alrighty? So, maybe don't write down all this slide. What I'd like to do is just talk you through this slide, and I'm going to go to Smart Notebook and solve the problem for you. I mean, if you wrote down anything, the first bullet point, calcium sulfate has a solubility of 0.67 grams per liter. If I gave you that value, you could solve for the K value of calcium sulfate. So one type of question that you could see is me giving you the solubility and asking you to solve for K. By the way, when I look at that solubility table for calcium sulfate, it is an I, it's insoluble. Remember, insoluble is a simplification. I could actually dissolve 0.67 grams of calcium sulfate in 1 liter of water. So I could take just a tiny little dusting. A pinch of calcium sulfate could be dissolved in water. When we solve this question, what I'm going to show you is I'm going to divide this into 3 steps. If I start with my grams per liter, how many grams can I dissolve in 1 liter? I can convert that into how many moles I can dissolve per liter. That's what molar solubility is. Then from there, I can figure out the concentration of each ion. And once I know that, notice for step number 3, I'm mentioning an ice table can be used. And I can solve for KSP. So again, I'm going to kind of switch over here. My step number 1, so I have 0.67 grams per liter of calcium sulfate. I want to get to moles per liter, because moles per liter, recall, is molarity. If I want moles, I got to put moles on the top of my conversion, grams on the bottom in order to cancel out my units. If I look at my periodic table, 1 mole of calcium sulfate is 136.15 grams. So step number 1, if I told you 0.67 grams of calcium sulfate can dissolve in 1 liter of solution, that'd be equivalent to a molarity of roughly 0.005 molar. So in other words, I can't make a more concentrated solution than that for calcium sulfate. That's as potent as it could be. After that, if I add any more, it's going to all sink to the bottom. It's going to be saturated. Now, when I look at this expression, if I would report it as a 0.0049 molar calcium sulfate solution, there's 1 calcium for every 1 calcium sulfate. Are you okay with that? Coefficients in front are all 1. There's 1 sulfate for every 1 calcium sulfate. If before I started the dissolving process there was 0 parts of both of these, once I started adding calcium, I'd be gaining a certain amount. Now when you did ice tables for weak acids, our textbook would use the letter X as the change. They use the letter S for this because now it's solubility. If you want to use the letter X for your variable, you go right ahead and do so. If you want to use whatever variable you want, you go right ahead and do so. So at equilibrium, I have an amount of S and an amount of S. Which means if KSP is the concentration of each product raised to their stoichiometric coefficient, I have S times S, which is the same as S squared. We use that 0.0049 value because for every one calcium sulfate, there's one calcium ion, so that's the S value. For every one sulfate, same thing, and we square it. That means the K value for this, I get as a 2.4 times 10 to the negative fifth. So in this first question, if I gave you solubility, how many grams could be dissolved in 1 liter? You could convert that to what's called molar solubility. All I do is convert my grams into moles. And then since everything in this one was a nice 1-to-1 ratio, that molar solubility that I solved for up here is 0.0049, that was the value for my calcium ion. That was the value for my sulfate ion. So all I had to do was square it. And again, if we try to think of, well, what could I see in a test? Well, maybe on a test you could be given a value as simple as 0.005. So that is something where you can multiply 0.005 times itself, hopefully. You know how to do 5 times 5 and then move decimal a few spots over. All right, so one way we can solve for this is you're given solubility, you want to solve for K. Move over. Second way we could do it is you're given the K value. Notice how small this K value is, by the way, 10 to the negative 20th. That must mean that copper 2 hydroxide, you can barely put any of that in water compared to the previous problem with the calcium sulfate. But if I gave you the K value, you could solve for the grams per liter, the solubility. So what I wanted to do with notes today was show you one of each direction. That way, when you're doing WebAssign, you can now do either problem. So if you want to just write down the beginning of solve for grams per liter of copper 2 hydroxide, and here's the K value. Again, I'll show you these 3 steps on Smart Notebook then. And even though you guys don't have a lot of time to practice this today, next class should be a little bit lighter of a day. I mean, besides all the pretty colors that you're going to see in the ooh and ahhing, you can be doing this type of math also. All right, so this next question was dealing with copper 2 hydroxide. And that solid breaking up into its ions. If I were to set up an ice table, initially, again, before I start adding any of that copper 2 hydroxide to the water, there's no copper ion or hydroxide ion present. But at some point, when I start adding, I'm going to be gaining those ions. I will gain an amount, again, to stay consistent with the textbook, I'll call it S of the copper ions. What do I put down for the gain for the hydroxide? 2S. Take into account that coefficient, which means at equilibrium, I'm going to have S and 2S. This is the second way that you might get tripped up on these types of problems, is the 2 part. Remember, if I were to write the K for this, it'd be the concentration of copper times the concentration of hydroxide squared. I have to take things to their stoichiometric coefficient, which means when I plug in my equilibrium values, I have S and I have 2S squared equaling my KSP. Again, the ice table is just to organize your data a little bit, remembering the stoichiometric coefficients, things like that. Remember, the question gave me the K value, 2.2 times 10 to the negative 20th. I can simplify my right side of the equation, 4S cubed. Distribute that square not only to the S, but also to the 2. That is a mistake that's pretty common. That they will give you multiple choice questions that are fairly straightforward with the numbers you would plug in. However, some students would call this 2S cubed instead of 4S cubed. I mean, we could put that to the power of 3 earlier on too, and it could be even bigger than that. Divide both sides by 4, take the cubed root of that, and you would get an S value of 1.8 times 10 to the negative 7. So again, I'll do that little math for you. This S value, if I scroll back up to my ice table a little bit here, would be the concentration of copper ion, again that's right here, at equilibrium. I'd have to double it actually to say what the hydroxide concentration is. But if we started this question by giving you the K value of copper 2 hydroxide, and we want to know what's the molarity of copper 2 hydroxide, the copper 2 hydroxide is in a 1-to-1 ratio with the copper ion. So this is the molarity. So in other words, what's the most concentrated copper 2 hydroxide solution I can make? 0.0000018 molar. That's why it precipitates right away. If, however, you wanted to solve for the solubility, I'd have to do one more step. I'd have to convert this to grams. Periodic table says that this is 97.57 grams. Solubility of copper 2 hydroxide is 1.8 times 10 negative 5 grams per liter. I could add 0.00018 grams of copper 2 hydroxide to a liter of water, and that's the most I could dissolve.